So this time, so we will learn about how the exceptions are handled in the processor. And then actually this is the last topic in the pipeline, the process architecture in this course. So the previous class we learned about the branch predictor. Okay, so this is the it's a so branch predictor uses the prediction technology, so which means that if the prediction hit rate, so it means that if the prediction is correct, then it may be hit, and then if the prediction is incorrect, the prediction result is incorrect with the real result, then it means miss. Okay, so if the hit rate, hit rate is high, then we can use our prediction technologies. And then also I mentioned that in the modern processor, so there are so many prediction technologies. Okay, so many prediction technologies are applied. Okay. So we learned about the 1-bit and then 2-bit predictor. Then so we learned how the branch predictor works in the pipeline processor. Okay. And then we briefly learned about the exceptions and interrupts. So exceptions and interrupts are rare events. Okay. And then if interrupts or exceptions are detected, so it should be detected by hardware, and these exceptions and interrupts are handled by operating systems, the software, right? But hardware also needs to support exception handling or interrupt handling. So firstly, the hardware needs to detect exception or interrupt, and then the informations. So the required information needs to be reported to the operating system. Okay, and then let's see how. So let's think about the exceptions. The exceptions are kind of it's a rare event, but it's related to some errors. Okay, such as the divide by 0 or overflow or underflow. Okay, also if the hardware cannot understand the input instruction, and it's also kind of exceptions. So that is the unknown instruction. Okay, so and then exceptions. So I said that exceptions are kind of errors in instruction. So which means that we need to detect which instruction causes exception. Okay. So firstly, we need to identify. The instruction that causes an exception. Okay. Then how? How can we identify an instruction? Okay. So we can identify an instruction using program counter. So program counter is the address of an instruction. So firstly, if the exceptions are detected by hardware, then the hardware, it means processors, need to store PC of the instruction that causes an exception, okay, or interruption. Okay, so RISC-V also has the registers that can store the program counter of the instruction that causes an exception. And then this register file is called SEPC, which is supervisor exception program counter. So which means that if an exception is detected in a certain instruction, then the program counter of this instruction is stored in SCPC. Okay, and the exception is detected, but there are many kinds of exceptions. Okay, and then based on these the kind of exceptions, then the operating system needs to call different exception handlers. Okay, so which means that we need to know which exceptions are detected in the hardware. Okay, so we need to know the kind of exceptions. So RISC-V also has the register. Then this register name is supervisor exception code register. So which means that the kind of exception, the code of exceptions is stored in this register. And then the exception is detected. This information, the program counter and then the code of the exception are reported to operating systems. Okay, and then also the handler needs to be called. So which means the exception is detected, then this is the handler. This is the kind of software. Okay, and then this software handles the exception. So how do you cause the exception handler, which is required for handling detected exceptions? Okay, so these are required operations supported by hardware. So the exception is detected, the PC needs to be stored, and then the cause of the exception needs to be stored. Then the processor needs to call the exception handler. So as you can see, this is jump. Okay. So that's why the exception is very similar to the jump instruction. So actually, the hardware, the processor jumps to the program counter of the exception handler. Okay. So sometimes we can use the vector interrupt, vector interrupt. So which means that so the interrupts are caused by I/O devices. Okay, and then based on those I/O commands, then the hardware also load some vector information, and then also the hardware calls the appropriate interrupt handling. But as I mentioned, the exceptions for interrupt are very similar because those are rare events. Okay. Then this I explained. Okay. So let's see how the exceptions are detected in the pipeline processor. Okay. So as I mentioned, the exception is very similar to the the execution of control instructions such as jump instruction. Okay, so which means that if the exception is handled by the processor, then clock cycles are wasted. But it's obvious, right? It's very similar to the jump instruction. So it's very similar. So it's kind of a control hazard. Okay, because the clock cycles are wasted. Because so obviously the program counter is changed to the first instruction of the exception handler. And then also let's see how the processor handles the exception. So this is just the example. And then let us assume that this instruction add x1, x2, and x1 provokes an exception in EX stage. Okay, so which means that an exception is detected in the EX stage for this instruction. Whether this instruction is in the EX stage, an exception is detected. So As I explained, when an exception is detected, we need to firstly store PC and cause of exceptions, right? Then, what should we do for this instruction? So, an exception is detected for this instruction, and I said that exception is a kind of an error, right? It's a kind of error in an instruction. So which means that this instruction needs to be cancelled. Right? Because when an exception is detected for this instruction, that it means that this instruction may have an error. Okay, so this error instruction needs to be cancelled in the processor, and then operating system needs to analyze the exceptions, the detected exceptions, and then so which means that this instruction needs to be cancelled. So which means that this instruction cannot be executed. So if an instruction pass through instruction fetch to the write back, okay, write back is the last stage of the processor. So which means that if an instruction reaches the write back stage, that means the instruction is completed. Okay, but exception is detected when this instruction is in the EX stage, and then we need to cancel. So we need to avoid the execution of this instruction, right? So the cancel means, so if an instruction is canceled, it's flushed. Okay. So we learned how to flush an instruction, right? So if the bubble is generated in the pipeline registers, then it means that the instruction is flushed. So the exception is detected, and this instruction is flushed. Then how about the following instruction? So what does it mean? So we have a pipeline processor has 5 stages, right? So this add instruction is in the EX stage. So which means that in the instruction fetch and then either stages, there are other instructions, right? It's the following instruction 0 and instruction 1. Also, this pipeline processor has precedent instruction. So which means the memory is write back. So this is the add, and then this is another instruction, 2 and 3. And then the exception is detected and the add is in the EX stage. So these are following instruction, right? This is a later instruction. Then what should we do? The error is detected, so this instruction is flushed. How about these instructions? So I said when an exception is detected, then processor calls exception handler. It jumps to the exception handler, right? So which means these instructions are incorrectly fetched, right? Do you understand? Because after this instruction, after this add instruction, the processor needs to execute the exception handler. But because of pipeline architecture, these following instructions are incorrectly fetched and stored in the pipeline stages. So these following instructions are also need to be cancelled. You understand? So also flushed. Then how about these instructions? The formal instruction, like instruction 2 and instruction 3. These instructions are normal instructions, right? The correct instructions. You understand? So actually, this inst2, inst3, inst2, and add is here, and then inst1 is here. So these are formal instructions. Actually, the execution of these instructions, like inst2 and inst3, needs to be complete. You understand? So processor needs to complete formal instructions. Okay, so instruction 2 needs to be propagated to the right backstage. Okay, so this slide explains this process. So prevent X1 from being global. So it means so this instruction needs to be cancelled. So which means that X1 is not updated, right? And then complete previous instruction. What are previous instructions? These instructions are previous instructions. And flush, add, and following instruction. Okay. And then PC and then as code register values. So as PC and codes of these exceptions are stored in the registers, and the handler is code. So this information is reported to operating system. Okay. So when an exception is detected, then following instructions are flushed. So which means it's very similar. The behavior of this pipeline processor is very similar to the mispredicted branch. Okay, because the following instructions are and its own instruction are cancelled, flushed. Okay. Okay. So this is the pipeline architecture that supports an exception. But actually the exception handling. So in order to support the exception, so it's rather complex. Okay. But in this video, we just show the exception that is detected in the EX stage. So as you can see, you can find as codes and SCPC registers the EX stage. Okay. So actually, the exceptions can be detected in the many other stages. Like the exceptions can be detected in the instruction batch or instruction decoding or memory also, and then like that. Okay. But in this example, I just showed I just assume that the exceptions are just detected in the EX stage. Okay. And then there are two kinds of exceptions. So it's restartable exception. Then sometimes we cannot the programs cannot be recovered from the exception. Okay. So restartable exceptions means that even though the exception is detected, then the exception handler is executed, and then after that, the program can also execute the certain instruction. Okay. So which means so in this example, add instruction. When the add instruction is in the EX stage, then an exception is detected. Okay, it's a kind of error. Okay, it's a kind of error. But if the if this exception is restartable exception, then firstly, the handler is called the COSE handler, and then after the handler is executed, then same instruction is fetched again. Right? So this is possible because we already stores the program counter of this add instruction. Okay. So in this case, the add instruction is fetched again, and the program can be restarted. Okay. So, and then, but if the programs cannot be recovered from an exception, then the program is terminated. Okay, and then operating system just provides the information of information regarding to the exception. Okay. Okay, so this is the example. So this is exception example. So as you can see, this is the program counter, right? It's a program counter, and so this is a program counter, and then you can find the instructions, and then let us assume that the exception is detected for this add instruction. Okay, and then this is the handler, the exception handler, and then this is the first PC of the exception handler, which means that if an exception is detected, then the processor needs to jump to the 1C090000. Okay. So, and then if we see this instruction, then let us assume that the exception is detected when the add instruction is in the EX stage, then OR instruction is in the memory stage, right? And is in the write back stage, right? And so is in the ID stage. The load word is a load instruction is in the instruction fetch stage. Okay. So in the pipeline diagram, you can find which instruction is in the which stage. Okay. So as I mentioned, add is here, and the OR is here, and is here, then solve is here. Okay. And then exception is detected. And then it's after 1 clock. So as I mentioned, and the instruction needs to be flushed, and then following instructions, sub instructions and load instruction need to be flushed. Then how about these instructions? These instructions need to be completed. Okay. So after 1 clock, so this add instruction is flushed. So you can find bubble here. So this is the bubble chain bubble add instruction, because add instruction is flushed, and then this is the bubble which instruction? The sub instruction is also flushed, and then this is the bubble by load instruction. And then we can find the OR instruction is here. So OR instruction is completed. And then as you can see, you can find the first instruction of the exception handler. Okay. This exception is fetched. The first instruction of the exception handler is fetched. Okay. So this I explained how an exception is handled in the pipeline processor, right? And then multiple exceptions can be detected in the same processor. So it can be possible. So there can be multiple errors in our code, which means that the multiple exceptions can be detected. Then, how can we handle these multiple instructions, multiple exceptions? So, for example, so in this example, we assume that only one exception is detected, while these instructions are in the pipeline processor, right? But there can be multiple exceptions. So for example, exception is detected for add instruction, and then at the same time, exception can be detected for solve instruction, and the solve instruction is in the ID stage. So there are two exceptions. So exception. So exception 0, exception 1, x0 and x1. Then what should we do? So I explained that when an exception is detected, add instruction needs to be flushed, and then solve and load instruction needs to be flushed. But in this example, there are two exceptions. What should we do? So when an exception is detected in the processor, then the exception information needs to be reported, and then also the exception needs to be handled. But these exceptions need to be handled the order of instructions. It means, firstly, this instruction. If we just consider the order of instruction, add instruction is the former instruction, the precedent instruction. In this case, even though the multiple exceptions are detected, the processor needs to handle the exception of former instruction first. Okay, so which means that adding. So in this case, firstly, the add instruction is handled. The exception of add instruction is handled. So, even though the exception is detected, solve instruction is flushed, and load instruction is also flushed. And if this is the restart of exception, then add instruction is fetched again. Then what will happen? The exception is handled, so which means that this exception is not detected because the exception of add instruction was already handled. Okay? But the exception of solve instruction is not handled, which means when the solve instruction is in the ID stage, x1 will be detected again. So in this case, exception is detected for solve instruction, and exception is handled. Okay? Exception handler is called again. So solve instruction is cancelled, and load instruction is cancelled, then x1 is handled. So you need to remember that exceptions need to be handled in the order of instructions. Okay. So this is the actually this kind of exception handling is called precise exceptions. Precise. So precise exceptions means that exceptions are handled in order. So in the order of instruction. Okay. Then, so you may think, oh, then what is the other case? So I mentioned precise exceptions. So which means that exceptions are handled in the order of instruction. Then what kind of other exceptions? So imprecise exceptions. Okay. Oops. Imprecise exceptions. So which means that in the imprecise exception, the exceptions cannot be in the order of instruction. So it is because the modern processors actually support out of order processing. And sometimes some processors cannot support precise exceptions. So in this case, the imprecise exceptions. So actually, the exceptions are just reported to the operating system. That operating system just estimating the problematic instructions. Okay, but most processors actually support precise exception. Okay, so you need to remember that when the multiple exceptions are detected, then exceptions need to be handled in the order of instructions. Okay, actually this is very important. And then in order to support the precise exceptions, then hardware also the hardware cost can be increased. So which means that we may need to invest more hardware resources to support precise exceptions. Okay. So but don't worry. So actually, the modern CPUs support precise exceptions. Okay. So sometimes the imprecise exceptions are so some processors support imprecise exceptions. Okay. So this is the end of the pipeline. So chapter 4, the pipeline architecture, and then so actually, as I mentioned, so this is the a very important part of this course. So which means that you need to understand how the pipeline processor works. Okay. And then also you need to understand the baseline concept of pipeline. So this is very frequently used in the hardware design. Okay. Okay, so let's move on to the next chapter. Memory systems. So also this is the a very important topics in the processor architecture. Is a memory hierarchy. Okay. So introduction. So actually the memory is a very critical part in the computer systems, right? Because our data is in the memory systems, right? And then we also store instructions. So instructions are also stored in the memory, right? And then the processor reads the stored instructions or stored data from memory, and then the processor executes instructions. Okay, so which means that all required data or all required instructions exist in the memory of a computer system. So memory is a very critical part. It's a very important part. Then where is a memory? In the computer system. So actually the CPU is here, right? So where is the memory? Okay, so this is very old computer, right? So memory is here. Okay. So actually the traditional computer systems, actually desktop computer system, we just insert memory DIMMs in these DIMMs now. Okay. So memory is here, but this memory is the DRAM, the main memory. Okay. And then, as you can see, this DRAM is the outside of the processor. Okay. And what's the problem? If a certain part is outside of a chip, because this is a chip, then it will be very, very slow. Okay. Then what's the problem? Problem is, so this is the diagram of pipeline processor. And where is a memory? Where is the memory? Memory is here. And this is an instruction memory, right? And then memory is here. This is a data memory. Right. So I mentioned in the computer system, the memory can be slow. But when we learned about the process architecture, then we assume that the data in the memory, so we can read instructions in the instruction memory, and then we can read data in the data memory. But we assume that this data can be read quickly. So it means, for example, so we need to read instruction from this instruction memory, but we do not consider the time. So which means the latency of this instruction memory. So which means that the time that will be taken for reading instruction from instruction memory. So we assume that we can read instructions within one clock cycle. So which means that we can read instruction very quickly. Data memory is the same. When the load instruction is executed in the memory stage, then we assume that this load instruction will take only one clock. So and then the clock frequency of the modern processor is kind of 5 gigahertz. It's very, very fast. So it means, which means that clock period is 0.2 nanosecond. 0.2 nanosecond. It's very, very short, very fast. And then it means in the process architecture, we assume we can read required data less than 0.2 nanosecond. It's very fast, okay? Extremely fast, but it's not possible. As I mentioned, actually, we store most of our data in the DRAM. It's the external memory. Each external memory is that the memory is located outside of a CPU chip. And then it will be very, very slow because it's outside of the chip. But processor works very fast. The clock period, the modern processor, the clock period is very, very short. It's not possible to read data within one clock. Okay, so What's the problem? The processor requires data for executing instruction. And then this data needs to be read from memory, but memory is slower than processors. Okay? Processor is very fast. It's very fast. Memory is slow. But processor needs to read data from the memory. So, which means that in order to execute instruction, then processor needs to work with memories. But if a certain part is very, very slow, actually, the performance of entire system is determined by the lower part. Okay? That is the problem. So what's the problem? Because of slow memory, the performance of the computer system is degraded. Okay? That is the problem. So as I mentioned, the processor needs to interact with memory system. Right? So address is given and then the data is provided to the processor. So, but processor is very fast. Then is very slow. So this performance gap between a processor and a memory is called memory wall. So memory wall. So which means that the performance of a computer system is degraded by slow memory. Okay. So in this graph, you can find the years, time, and then also this is the relative performance by CPU and memory. Okay, in the very old times, so around the 1980, the performance is nearly the same. The memory, which means the CPU was also very, very slow in this time, very old. But as you can see, the CPU performance is improved exponentially. Memory performance is also improved exponentially. So as you can see, the linear graph, and this is the low scale, y-axis is the low scale. And then, so which means that the performance is exponentially improved. But what's the problem? The gap. The gap between the performance gap between the CPU and the memory system is also increased, exponentially increased. So that's the problem. Because of the slow memory, the performance of the entire computer system is also degraded. Okay? This is called the memory wall. This is very popular term in the computer system. Okay. Then how can we handle how can we handle this issue, the slow memory issue? So in order to overcome the memory wall in the computer system, we use memory hierarchy. What is the hierarchy? The hierarchy is actually the social hierarchy is the social terminology, right? Which is kind of 계층 구조 in Korean, 계층. So it's a kind of social level, social hierarchy, social level. So, but in the also like the social hierarchy, then we can just implement the memory system like a memory hierarchy. We can just implement the memory hierarchy, and then using this memory hierarchy, then we can overcome memory wall, which means that in order to overcome the the memory world, the slow memory, low performance of memory system, we use memory hierarchy. So it's very important. It's very important in the computer system. It's really important in the modern computer system. It is because the modern applications handle large amount of data. So think like this. Think like ChatGPT. So ChatGPT, the parameter size of ChatGPT is kind of a billion. There are billions of parameters in the ChatGPT. So which is, so those are kind of data. Okay. So actually, a large amount of data is handled by computer system. So it means the performance of memory is more critical, so more important. Okay, so then how? Firstly, so we need to understand the locality, principle of locality. So what is locality? So actually in Korean, it is translated into 지역성. So what does that mean? So locality means that, so actually the size is very large. Actually the size of the size of entire data is very large, but only the part of data is accessed again and again. So this is kind of locality. Okay? Which means that even though the entire system is very large, only the small part is repeatedly used. So you can understand that locality is, so locality means that in the very large system, only the small part is accessed. So this is kind of locality. So actually, the memory hierarchy uses to exploit locality of data. The locality of data. And then is also called the data locality. And then there are two kinds of locality: temporal locality and then spatial locality. So temporal means it's a kind of time. Then spatial is space. Okay. Then there are two kinds of locality, data locality. Okay. This locality is observed in our application. So then what is temporal locality? So time-based locality, so which means if a certain data is used, okay, the same data is repeatedly used. It's the temporal locality. So time is temporal, but the timing is different, but with the different timing, the same data is requested again and again. So we can observe this temporal locality frequently. For example, for I equal 0, and then I is less than 100, I plus plus. Okay. So in this iterative for loop, variable I is repeatedly used. Right. Also, instructions in the loop, like the add, sub, and then multiply in this loop. So instructions in the iterative loop is executed again and again, right? So also instructions are data, right? So same data is executed. Same data is fetched in the instruction memory. So data is accessed again and again. It's called the temporal locality. So what is the spatial locality? spatial represent the space-based. So spatial locality means that a certain data is accessed, like the A0, or A0 is accessed, then with the high probability, our program will access A1, obviously, right? So there are many elements in the array, then if we just access one element in the array, then the next element, like A1, will be accessed in the near future. So, which means spatial locality means that if a certain data is accessed, then near data, the near data will be accessed in the near future. Okay? So actually, we already know that. So if A0 is here, and then with the size of the element, then the next element A1 is here, and then A2 is here in the memory, right? So which means the near data will be accessed in the near future. So this is called the spatial locality. So in our applications, temporal locality and then spatial locality is frequently observed. If this is the characteristics of our applications, and then this locality is exploited in the memory system, actually in the memory hierarchy. Okay. Then what is the memory hierarchy? Okay, so I will show this here. So it's memory hierarchy. So it's very similar. So actually the shape of this memory hierarchy is very similar to the social hierarchy. If you learned about some social science, then you can find some social hierarchy like this. So we can observe various memory devices in the memory hierarchy. So what is RF? Oops. RF is the register file. Now everyone knows register file, right? So in chapter 4, we frequently so the register file. And then also I mentioned that the register file is very small and then very fast memory, right? Actually, we can just store the several word data in the register file. Okay? In the register file, we can store 32 integer data in the integer register file, right? And then you can find cache. So we'll learn about the cache later. And then main memory, the DRAM. Then this is the storage. And then also you can find the characteristics of these memory devices. So register file, as I mentioned, the register file is very fast. So which means that it's high performance. It's a high performance memory. So high performance means that this component is very fast and then low capacity. So in the register file, we can just store 32 words, right? So 32 and multiply by 4 bytes. So actually we can just store 128 bytes in the integer register file of this file. Okay, low capacity. Capacity is very low. and then high cost. It's expensive. So this small memory is here, and then execution engine, the processor is actually here. So near the processor, we can find there is small memory, low capacity, and then fast memory, the high performance. But how about the storage, SSD or hard disk drive? So recently we can enjoy very large storage devices such as 1 terabyte or 2 terabyte. So compared to it's 128 byte. It's 1 terabyte. What is tera? Kilo is 2 to 10 mega, 2 to 20 giga, 2 to 30 tera, 2 to the power of 40. So it's extremely large, right? So the high capacity, but performance is extremely low. So actually, so obviously we store our data in the storage devices. We store every data in storage devices. And then DRAM. So recently the DRAM is kind of gigabyte space, 4 gigabyte or 88 gigabyte. But when we launch a program, then actually the program is transferred to the main memory, so DRAM. So the required data. So actually the storage most data exists in the storage devices, but the required data, the program is launched, then the required data is read from the storage devices, and then only part of the data is stored in the main memory. And actually, the register file, the size of cache, we will learn about the cache later. The size of cache is smaller than the main memory, but the performance is higher. So in the register file can only store 128 bytes. So small amount of data is only transferred to the register file, and then this small amount of data is quickly accessed by processor. Okay, and then this data is used for executing instruction. So in the memory hierarchy, so we can find that in the lower level, so this is the low level. This is the high level. Okay. So in the low level memory, the capacity is very high, but it's very, very slow. So which means we can find our data in the low level memory. The high level memory, the capacity is very low, but performance is very high. So the register file, we can read data from register file within 1 click. It's very fast. Actually, we can use this memory hierarchy because of data locality. Why? So what is the locality? So I mentioned that this is the largest system. This is the largest system, but only part of the system. It's a very small amount of data or small amount of system resource is used. Okay, so this is the locality. So which means that I have a very large amount of data, but in the very short time, we only used the part of data. So which means we do not use this entire data in the shoot time. Which means, and then this data is small amount of data is repeatedly used again and again. Also, especially the closed data is also accessed again and again. So which means I mentioned the high-level memory is very expensive. The size is small. But because of locality, we can store frequently used data in the small sized high-level memory. And then, this data will be used again and again. Okay? So we can quickly access the data in this high-level memory. But we also require large-sized memory because we have a very large amount of data. This large amount of data is stored in the low-level memory. So very slow, but the capacity is very high. So, but among these large amount of data, in the short time, you need to use the part of data like this. Then this small amount of data is transferred to the high-level memory. And then because this small amount of data will be requested again and again. This small amount of data can exist in the high-level memory, and then processor can read the data from the high-level memory very quickly. Okay, so this is the memory hierarchy. So in order to use memory hierarchy, the locality needs to be observed. Okay, if the locality is not observed, then we cannot use memory hierarchy. Why? Let us assume that this large amount of data is used in the very short time, which means that we need to store this large amount of data in the high-level memory. But the high-level memory size is very small. It's not possible to store all data in the high-level memory. Okay, so because of data locality, we can use memory hierarchy. But the memory locality is not observed, and the performance will be very low. Okay? But fortunately, we can observe the locality most of the applications. Okay, so that's why we can use a memory hierarchy in our computer system. Okay, do you understand? This is very important. Okay. So when we in order to understand the behavior in the memory hierarchy, then we need to understand how the data is requested, and then also we need to understand the terminology hit and miss. Hit and miss. So I actually used this terminology, right? The branch predictor, right? So what is the hit? So hit means if the prediction result is same to the real result, so it is called hit or hit. The miss means that the prediction result is not equal to the real result. So also we use this terminology hit and miss. This terminology hit and miss in the memory hierarchy. Okay. So why? Let's see. So in the memory hierarchy, there are many various memory components at the high-level memory and low-level memories. Okay. So and then processor is here. So as you can see, processor is here. And then the processor requires data. Okay? So data is required, like data. Data include the instruction. Then the processor requests the required data to the highest level, which means high level memory. Okay. So actually the register file is a very special memory. So and then, for example, when the load instruction is executed, then the highest level of this memory is the level 1 cache. Okay. So when the data is requested, then the processor requests the required data to the high level memory first. Okay, so it means the L1 cache, the high level memory first. Then there can be two cases. Right. What are cases? So the size of this high level memory is very small. So which means that this high level memory cannot store all data. But a certain data is requested by a processor. Then there can be two cases. The request data can be found, fortunately, or the request data is not found. Okay, that can be possible, right? Because the size is very, very small. Only the part of data exists in this high-level memory. So I said the high-level memory, the processor requests data to the high-level memory. And then there are two cases. Oh, data is found, fortunately. So data is found. Then this data can be provided to the processor very quickly because high-level memory is fast. Found. This case is the very good case. And then this case is called hit. Okay. So in the predictor, the prediction result is the same to the real result, it's a hit because it's a good case. Okay. But if data is not found, this is called a miss. Okay. In the hit case, the data is provided to the processor in the high-level memory. But if data is not found, then the request is given to the lower level memory. Because the size of lower level memory is larger than the size of higher level memory. So the request is given to the lower level memory. So you need to understand, that the processor first request data to the higher level memory, and there are two cases, a hit case and then a miss case. The hit case means that the data is found in this high level memory. Okay, then the data is provided to the processor. But in the miss case, the data is not found, then the request is given to the lower level memory. Okay. So also, if there is a lower level memory under this memory level, then there can be also two cases, hit or miss. So hit rate. So we can define hit rate because hit rate is the number of hit of among number of total accesses. So which means that the processor can if request to this memory, or there are two cases, hit or miss hit. So and then hit, so which means that the number of hits is less than the number of accesses, right? So and then we can define hit rate as the number of hits over number of accesses. Okay. So if the hit rate is high, then if the hit rate is high, which means that it's a good cases, right? Which means the data is the request data is provided by higher level memory. More, okay? More data is provided by higher level memory quickly. So which means if the hit rate is high, the performance can be high. Okay. So hit ratio is the number of hits per accesses. And then we can also define this rate. So obviously this rate is the number of misses over number of accesses. Okay. So this rate is high, performance will be degraded. Okay. And also in the miss case, then we need to the processor needs to access the lower level memory. Then the lower level memory is lower than the higher level memory. So which means when the data is fetched from the lower level memory, so it will take longer. So this longer time is called the miss penalty. So which means that miss penalty means that in the miss case, then it will take more time compared to the hit case, and then this the more time is for the miss penalty. Okay. So you need to understand that this common rate, like hit or miss is very important. The hit or miss, or hit rate or miss rate, or miss penalty. So actually you need to understand the definition of this terminology to understand the behavior of memory hierarchy. Okay. Okay, so I will stop here. Then the next class, I briefly explain about the various memory techniques. Any questions? Come down.